Thank you. I'm excited to be here. Cool. So I'll talk a little bit about robotics. Michael already set the stage great, so we can continue from there on. To put it in context, I think when we talk about video agents nowadays, at least on Twitter, it's often video agents in the digital world. But for today's talk, as I mentioned, we will look at the physical world, and specifically at video agents that can do a lot of dexterous real-world manipulation tasks like the ones you see in this video. Generally, the approach that I take to solving these problems, and that many of my colleagues take too, is the large data approach to physical agents, which means that we typically work with large real-world robot data sets, like this one called the Open Cross-Embodiment Dataset, which we released maybe 2 years ago at this point. We use them to train generalist policies. So those are policies that can perform many diverse real-world tasks out of the box, most likely on multiple robots. And they can, like any good foundation model, also be efficiently fine-tuned to solve new tasks or work with new embodiments. Okay, so it looks very much like a foundation model approach in other domains. And one of the big learnings over the last maybe 2 years in robotics is that this scaling approach to robot learning actually works. So this is a fairly recent result that we published a few months ago called Pi'05, where essentially we have shown that as you increase the number of environments in which you collect your training data, the performance of robots performing these somewhat complex and long horizon kitchen cleanup tasks actually improves. And in the limit, it kind of approaches the performance of policies trained with data from the target environment. So basically, this robot is operating in an environment that it has never seen before. But because we have pre-trained it on lots of data from many different environments, it is able to perform in this new environment roughly at the level of a robot that has training data from that environment. Okay, so data scaling works, at least to some extent in robotics. Now, the question I want to focus on in today's talk mostly is how can we design models that are actually able to train on large-scale robot data sets and then perform these kind of complex tasks. All right. Again, over the last 2 years, and I think Michael has already talked to this a little bit, the kind of dominant architecture that we have been developing for training scalable robot models has been based on architectures developed outside of robotics, specifically vision language models. So vision language models are great for robotics because they already are multimodal. So they take images as input, they take language as input, and they're very scalable, plus they come with some web-based pre-training knowledge. Okay, and the robotics problem actually looks very similar to a VLM problem, because what we want to train robot models to do is to map from images and language instructions to some action output, basically something that we can put onto our robot and then have it move in the environment. Okay, and so the step from a vision language model to this kind of vision language action model isn't particularly large, really. But the only thing we need to do is kind of figure out a way to represent the actions such that our vision language model can predict them. Then we can take a vision language model, fine-tune it on our robot data, and get it to control our robot. Okay, and so the dominant architecture for scalable robot learning over the last few years has been vision language action models. And so most papers you see today that do large-scale robot learning are based on essentially this idea. Why is that the case? Well, we have actually seen these models perform really well. So this is an experiment we did roughly 1.5 years ago in a paper called OpenVLA, where we built an open source version of such a vision language action model and had it control a bunch of robots. You can see these tasks here. They're like fairly simple tabletop manipulation tasks. But what we found, importantly, is that, as you see in these graphs, essentially the previous generation of robotics models, which were fairly standard non-pre-trained transformer models, is significantly worse in performance, or to say differently, the VLM initialized models are significantly better, even when trained on the same robot data, than their previous version non-VLM initialized competitors. Okay, and this is the OpenVLA model I mentioned, the RT2 model, I think Michael also mentioned before, as a model from Google. And really the main difference is that these VLM initialized models are significantly better than the previous generation, both out of the box and when you fine-tune. Okay, and so this is the reason that most people in scalable robot learning today work with these VLA models. All right, so this is all exciting. Now, roughly 1 year ago, we found this company called Physical Intelligence, and we tried to take this approach and then have it do harder tasks, essentially things that are a bit more dexterous than tabletop pick and place, things like laundry folding. And so we took the OpenVLA style model and we fine-tuned it on this kind of laundry folding data. And what you see here is that it doesn't actually work. Right? This video, I sped it up 40 times. If you run this in real time, it's excruciatingly slow. And also the thing doesn't do a very good job at actually folding the shirt. Okay, so the conclusion from this first experiment for us was that the version 1 that we had developed, the vision language action models, things like RT2, OpenVLA, aren't actually able to perform very dexterous manipulation tasks, and they're particularly slow if you want to run them on the real robot. Okay, so there's a lot of excitement about VLAs, but this version 1 isn't really cutting what we want these VLAs to do. So in today's talk, I will focus essentially on the version 2 of VLAs, which are more dexterous, they train faster, and they inference faster than the version 1 VLAs, and they're actually able to perform a lot of these kind of more complex tasks. And I will go into the technical details of how we went from V1 to V2. And then towards the end of the talk, I also want to hopefully motivate a lot of you guys to consider working on VLA-style robotics models. And I want to talk a little bit about how anybody, even without a physical robot at their availability, can contribute to robotics research. And I think there's a lot of opportunity in today's research landscape. All right, so let's talk about how we can go from VLA V1 to VLA V2 and what we need to do to make these models actually dexterous. And the main issue, as we fairly quickly figured out, is how we represent actions when we train the models to predict those actions. Okay, and in the V1 VLAs, we kind of did a fairly ad hoc job. We essentially just did anything that seemed reasonable to get the actions into the model. But as it turns out, this is a really important choice about how do you represent actions. Because if you look at it on face value, this is the only thing that we do differently from VLMs. We introduced this new modality, so how we introduce it really matters. Okay, how do OpenVLA and such models represent actions? The typical approach is very simple. You take your continuous robot actions for a single arm end effector controlled robot like this. It may be something like a end effector translation, rotation, and a gripper open close command. This is what a typical action looks like. This is a continuous valued quantity. But then in order to train kind of autoregressive VLM style models on it, we need to quantize it. We need to essentially tokenize it. Okay, and what we do in models like OpenVLA is that we take the range of values in your training data set over each action dimension, and we bin discretize it. So like the stupidest thing you can do, essentially just like take your range, divide it into a uniform number of bins, and then whenever a new continuous value comes in, you essentially check which bin it falls into, and that's a discrete token value that you assign to it. Okay, very simple binning tokenization. Okay, why is that an issue? Well, what happens is, typically we don't actually train these models to just predict one action. We train them to predict what we call an action chunk, which is essentially something like a second's worth of future actions. This helps with the robot acting a bit more smoothly than if you just predict one action at a time. Okay, and if you have these simple kind of OpenVLA style pick, place, tabletop manipulation tasks, we typically do them at low frequency, maybe like 3 Hertz control frequency. So you have 3 actions that you need to predict in this 1 second chunk, and you end up with a target action token matrix that looks like this. But now what happens, if we want to do more complicated tasks, we typically increase the control frequency, right? We make the robot more reactive by sending more action inputs per second. And so in our training pipeline, what this does is that it essentially increases the number of things we need to predict in this action chunk. Okay, so your token matrix essentially gets more columns. But now the problem with that is that as we sample this continuous time signal at higher and higher frequency, we essentially increase correlation between those samples, right? It's a very natural thing that happens. If you sample a continuous signal at higher frequency, correlation between your samples increases. And what this means in practice is that we find in our token matrix, there's a lot of similar tokens. And this is plain English what happens. Okay, so higher frequency means higher correlation. Why is that an issue? Well, the way that we train these models is with a next token prediction objective, right? Where we essentially flatten that matrix and then we do all previous tokens to the one next token as our training objective, like we usually do in VLM land. But now the problem is if those tokens are highly correlated, then there isn't a lot of information in that next token prediction objective, right? Your new token essentially looks like most of your previous tokens. Okay, and if you have very correlated tokens, then essentially autoregressive model prediction turns out to not train very well, right? Because your objective is the next token prediction objective. There isn't a lot of information in the next token. So training stalls, inference stalls, the whole thing doesn't work. Okay, so to summarize this fairly technical discussion of why previous models don't work, essentially at high frequency, we end up with a lot of low information density tokens. And when we train on them, then training stalls. So what can we do? Well, clearly, we need to do something better in how we represent actions. And so I want to introduce to you guys 2 different approaches that we have kind of experimented with in parallel to solve this problem. And then in the end, we can see whether we can somehow meaningfully put them together. The first idea that we had in a paper called Pi0 is that, well, what we want to predict are continuous valued actions, right? And we kind of went through this distorted way of trying to tokenize them so that we can get them into the discrete representations VLMs work with. Why not instead try to actually make models that predict continuous valued quantities? Okay, and so the simple idea here is that you take that VLM backbone, but you add new weights for continuous prediction, what we call an action expert, which is essentially a diffusion decoding head. So that is a new set of weights that we add to a pre-trained VLM backbone that is only there to predict continuous actions through a diffusion decoding objective, flow matching in the case of this particular paper. And it cross-attends to the VLM backbone. Okay, so we have new weights, they're there for continuous action prediction. We don't need to tokenize, and so we can train that very efficiently on the continuous targets that we're trying to optimize for. Okay, this works really well. Here are some of the results of that paper, Pi0. Essentially, we can now take these VLM models and we can have them actually solve continuous and dexterous tasks. You can see here, they can do laundry folding, they can do build a box, which is a really hard kind of long horizon task. And they can even do these things. This is like a 10-minute video, sped up quite a bit, of a robot actually doing a full stack of laundry in a row. And it's a very dexterous task. You need to like untangle the laundry, you need to fold it, you need to stack it. There's a lot of work that goes into it. But these VLAs are now able to do it, right? If I trained OpenVLA on this task, no hope that it would work. In fact, we tried, and it's very hard to see OpenVLA in this plot because it's basically a flat zero. Also, Octo is kind of the even previous generation of robotics model also doesn't work at all. So really figuring out how to represent actions for VLAs is very crucial to make them work on these complicated tasks. So what we got with the Pi0 model is a model that can do dexterous tasks. What we didn't get is a model that trains fast. Turns out this kind of diffusion training objective is really slow to train. So we need to spend lots of compute on our large data sets to make it work. And because we introduced a new set of weights, we turn out to lose quite a bit of that pre-training benefit that we wanted to get from the VLM. Right? So for example, these models turn out to follow language much worse. And so we kind of went back and we tried to figure out, well, is there a different way that we can address this problem that I had introduced earlier without needing to introduce the specialized diffusion decoding head for actions? And if you remember, the real issue that we had here is that our tokens are essentially not information dense enough, right? They're kind of not enough information each token, so autoregressive training doesn't work. Well, the simple idea we had to fix it is we can actually try to compress our action tokens, right? Compression just means you reduce the number of tokens, but you increase the information per token. And why does that help? Well, if you have more information per token, then this kind of autoregressive training is actually more efficient because now your next token prediction objective actually has a lot of things to predict and learn from. And to be clear, we're not the first people to think about this, right? Like if you think about how language models are trained, everybody compresses their training data, right? Nobody trains on characters or bytes. Everybody applies some sort of byte pair encoding tokenizer, which is essentially a compression algorithm. Okay. Now for continuous actions in robotics, we can't really use byte pair encoding because it's designed for discrete data, so it doesn't work very well. So instead, we designed a new tokenizer based on more classic signal compression techniques, specifically a technique called discrete cosine transform, or DCT. You may not have heard of it, but it's actually used in your everyday life quite a bit, in JPEG compression, for example. And the way that DCT works is that you can take a continuous time input signal, like this action chunk, and you essentially apply a Fourier transform. You transform it into a mixture of fixed frequency cosine bases. And the really good property of DCT is that usually you can represent most natural input signals with just a few very high valued coefficients in these DCT bases. And then most of the other coefficients turn out to be zero. And that's why it's so great for compression. Okay, so we can use DCT to design a tokenizer for robot actions that is much more efficient by converting our continuous input actions into DCT coefficients. Do that for every action dimension in your robot action chunk. So you end up with a coefficient matrix like this. And importantly, that matrix is sparse. So it has a lot of zeros, which we can compress away. And that's how we essentially achieve compression. So we flatten that matrix, apply your favorite compression algorithm. In our case, we use byte pair encoding. And what you end up with after all of this pipeline is a short chunk of high information density tokens that represent our actions. Okay, so fast tokenizer is what we called it. Essentially takes your action chunk, compresses it into a short sequence of high information density tokens. But now importantly, once we did this, we can train the VLA v2 the same way we trained VLA v1, right? It's just the next token prediction objective, fits perfectly in your large scale VLM code base. You just change the tokens that you make the model predict. Cool. Does this work? We tested it again across a bunch of different robotics tasks, from simple to hard. And on all these tasks, we find that this new way of compressing robot actions does actually improve compression significantly. So compared to kind of the previous naive ways of tokenizing actions, specifically on these higher frequency tasks, we see a significant difference in compression. So we get away with much fewer action tokens, essentially. And this leads to significantly better training. So here we tried same VLM architecture, fine-tuned on the same robot data set, just different tokenization approaches. And what you can see is that the standard kind of open VLA style of tokenizing actions, sorry, I'm not sure why it's not clicking, doesn't work, right? We had established that before. But then when we train on the same data with our new fast tokenizer, we actually get these policies to train now. Right? There's no difference in model architecture. It's just a difference in the way that we represent the actions. We did also compare to vector quantization, which is a fairly standard approach people take in vision, for example, to tokenize things like images. It's a lot more complicated because now you need to train a neural network encoder and a decoder, and it turns out to not work as well, and it's harder to tune. So the fast tokenizer is really nice because it's easy and it works. We did scale this up. We trained it on a large data set that we have at Physical Intelligence. It can then also do these very complicated tasks, just now with a different modeling approach. The other, and maybe my favorite result from this paper, is that we actually trained a model on a large open source data set called Droid. And we were able to train a single checkpoint on Droid and then deploy it essentially zero shot to many of our collaborators' labs. So we just like train that checkpoint, we ship it to them, they run it on their robot, and it can do a bunch of different tasks simply by prompting it. Okay, and this is maybe something that is quite familiar to people working in like language modeling or vision language modeling, that you can just like download a checkpoint, prompt, it does something. I want to emphasize in robotics, this is not the case, right? Like if you take OpenVLA, you download it, you definitely need to fine tune it with data from your environment for it to work. And so this was kind of the first time that we were able to show that you can take a model, just prompt it, and it typically does something reasonable on your tasks. All right, final slide on this model is that we tested training speed. This is really crucial for us, right? We have lots of data, we don't have all the GPUs in the world. So how fast we can train these models really determines how many iteration cycles we can do in our experiments. And what we found is that compared to the kind of previous diffusion-based model, this simple autoregressive model trains 5 times faster, right? And so this is the difference between a few weeks per pre-training run versus a few days. Okay, so this is really important that this model trains so much faster because of the simple autoregressive prediction scheme. All right, so where we are right now for VLA v2 is that we have the diffusion expert solution, which gives us very dexterous tasks, but it trains slow, loses pre-training benefits. We have the autoregressive plus nice tokenization solution, which does solve dexterous tasks as well. It trains fast, it learns good language following. However, the dirty laundry that I haven't talked about is it's really slow at inference time, right? Like this autoregressive prediction objective where you need to predict these action tokens still is pretty slow. Even after you compress the actions, it can typically take between half and 1 second to predict 1 second worth of robot actions. Whereas the diffusion-based models, they are quite fast. They can typically get away with like 100 milliseconds. All right, so final question of this section of the talk is, can we get the best of both worlds? Can we somehow get something that trains fast and follows language well, but also actually runs fast on the robot? And well, luckily, the answer is yes. And the solution is actually very simple. You can simply take the 2 solutions we came up with and you can put them together. Okay, so essentially we can train a VLA with discrete action token targets. But then we can also introduce that same action expert that uses diffusion decoding. Just crucially, we make sure that none of those pesky diffusion gradients go back into our nice VLM backbone. Okay, we just add a gradient stop during training. And what that does is it essentially uses the fast discrete tokens as your representation learning objective, right? That's what you train your VLM backbone with. But then you still train that diffusion expert as your inference model. So during inference, we use the diffusion. During training, we train with both, but really most of the gradients come from the discrete action targets. Okay, and by putting things together in this way, we do get the best of both worlds. So we get fast training. You can see we can match the training speed of the discrete model here, much faster than the diffusion model in comparison. We do get good performance, so the thing still works well on the robot, and we get fast inference. So here you can see that our method in yellow is much faster at completing the tasks than the original discretized model in this beige color here. Okay, and this is the base model that we designed to actually solve a lot of these kind of complicated robot tasks that we then showed You can do, zero shot in new environments, doing things like this towel hang task, which actually turns out to be very complicated because you first need to fold the towel nicely, but then also, hopefully it will do it now, you need to kind of like very carefully maneuver it inside this hanging, this oven handle. Okay, so these are hard tasks. We can do them in unseen environments just by prompting the model to do them. So this is quite nice. I do want to emphasize we haven't solved robotics yet. These are still a very small set of the kind of behaviors that we would want robots to perform. Success rate is maybe 50 or 80%. So don't overhype it, but I think it is a nice sign that these models do generalize to new environments. All right, key takeaways. What we have essentially shown is that a new generation of VLAs can be designed that does scale, but importantly, it also is able to solve dexterous manipulation tasks, which was not true for VLA version 1. And the key techniques, as I had mentioned in today's talk, to achieve this is essentially diffusion decoding for fast actions and autoregressive decoding for fast training. All right, final slides of the talk. I hope that I could get you guys a little bit excited about VLA research, about robotics research in general. Now, being at a vision conference here at CVPR, I may suspect that some of you may not have access to real robots. And so, it's a bit unclear how can you contribute to this research direction. But I actually think there is a lot of potential here because hopefully, as you have seen, VLA models are essentially VLM models, right? These things are not so different from the things that people work on in vision. And so I think there's a lot of transfer that can come from the vision community into the robotics community. But so the key things you need to do research are things like data sets, models, or evals, right? And so how do you get those for robotics? But over the last 2-ish years, we have done quite a bit of work on trying to lower the entry barrier into the field of robotics. So we have open sourced a lot of the data sets that I have talked about today. The Droid data set that delivered this zero-shot generalization to new environments is a fully open source data set. You can download it today. All the models that I have talked about today are public. Well, most of them in a repository called OpenPy. We have released the Pi0 model. We have released the Pi0 fast model. We are working on releasing the Pi0.5 model. So all of these things are available for you today. And then on the eval side, we have worked on projects that make eval easier. So we have released simulated environments that are pretty close to real. So you can actually test your policies in those environments, and it is somewhat informative about their real world performance. And we have also worked on real world evals where policies evaluate other policies. So this is a fully automated setup running at UC Berkeley with these kind of very busy robot arms here. And you can submit your policies to these work cells from anywhere in the world, right? You just like upload your policy. We will run it on our robot. You will get back your numbers. You can put it in the paper. Okay, so we are working on making this easier for everyone. And we have a few more works in the pipeline that hopefully further lower the barrier to entry into the field of robotics. But I hope that this is some motivation for you guys to try and contribute, because I think there's a lot more work to be done. Cool. With that, I want to conclude. I want to thank all my many collaborators at Pi. I want to specifically point out the contributions of Kevin, who has worked a lot on the Pi0 model. Karl has worked with me as a co-author on the fast approach to tokenization. And then Danny has kind of put these things together and shown that we can get the best of both worlds. Excellent. With that, I want to thank you and happy to take any questions. Thanks.
I'm trying to understand why the diffusion, when you combine it with the VLA, ends up being faster at difference time. Like, what part of the VLA do you no longer run?
Yeah, you don't run the discrete, like the autoregressive action decoding. So basically, you do run the backbone. That's one forward pass, right? Because it's an encoding, it's not decoding, so you can do it in parallel. But then the slow part is the autoregressive decoding, where you need to do like 60 steps or so to get an action chunk. And so we don't do that anymore, but instead we just take the diffusion model as the decoding mechanism. A diffusion can be slow, but in practice, it turns out that we can get away with a smaller backbone for the diffusion side. So it's less weights. And you only need to do roughly 10 diffusion steps to get a good output instead of 60 autoregressive steps with the discrete decoding. And so that's how you get from 0.7 seconds per action chunk down to like 0.1 seconds. Yeah.
Just a quick follow-up. So at inference, you just throw away the autoregressive prediction.
That's right. So, in actual practice, what we do is a little bit similar to what Michael actually presented earlier, is that we make the model first predict kind of language-based subtask things. And so those we still use autoregressively at inference time, but then for anything action-related, we only use the diffusion decoding. Yeah.
question about the reactiveness of the policies, because you said, for example, for a folding, you use 50 hertz, but then you also mentioned that there's like a 100 milliseconds inference time. So what does reactiveness actually mean in this case?
Yeah, great. So yes, so the training data is 50 hertz. The way the policy is trained is that you typically predict a 1 second chunk, so 50 actions. The way it's inferenced standard is that you predict half of that. It's a hyperparameter, but typically we predict half. So for 0.5 seconds, it's essentially an open loop policy. So it just like runs the 0.5 plan and then it replans. Just this week or last week, we released a paper also authored by Kevin Black, who I mentioned in the end, on doing a little bit more smart inference time, kind of interleaved prediction and inference or an execution. And so there you can get the reactiveness to actually be lower than half a second.
So the actual inference speed of the model then.
Exactly. So basically then you can get down to like maybe 100 milliseconds. I don't think we have fully pushed this down further. Most of the tasks we're doing are still fairly static, right? Like it's, the shirt doesn't move too much. There are certain parts of the task that are dynamic. So for example, when you fluff the shirt to flatten it, you need to kind of move continuously, right? If you move halfway and then you wait half a second to predict the next action and then you move, then it doesn't work. I expect that if we do more dynamic tasks, like maybe the environment is moving, there's an agent in the environment, whatever. In that case, you may want to get faster. And then I think we need to see whether we can quantize the models, make them smaller so that they run faster. Yeah.
Do you see any benefits in these like system 1, system 2 kind of?
Yeah, actually the Pi 0.5 model was evaluated in a system 1, system 2 way, where the high level subtask predictor runs like every 2 seconds or something, and then the low level runs at 10 hertz. So yeah, I think you can see benefit there, but you need to kind of be a little bit smart in how you disentangle the levels. Yeah.
Okay, let's thank the speaker again.